Hello once again, AP Calculus AB students. We are still taking a look at section 9.3 out of Larson's 9th edition textbook when we're dealing with the integral test. Later on, the section does go on to discuss the P-series type of series as well. In our example 1, part B, which isn't yet to be written out for you, but we'll take care of that right now once we pick the pen that I want. What we're going to look at is the summation from 1 to infinity of the nth term expression given by 1 over n squared plus 1. 1 over n squared plus 1. Now, our job here is to confirm whether the integral test, first of all, can be applied. And if you've done a little bit of research on the integral test up to this point, hopefully you've determined that there are 3 different criteria, right, that have to be met in order for the integral test to indeed work. And the first of which is to determine whether or not the 1 over n squared plus 1 in this case will take on a positive value for n being greater than 1. Now, typically what I will tell my students to do is to simply allow f of x to sort of take over. In other words, rewrite your nth term expression as a function f of x. Just swap the x out for n. There's no harm in that, and I think most students will probably feel more comfortable dealing with x than they would with n anyway. So we have to just verify that this is positive. And I'm not talking about going through a bunch of hoops to do that. I mean, just think about this. This guy is always going to be positive for values of x that are going to be 1 and bigger, right? Because remember, our x is like our n, and over here we have a 1 where our index is going to begin. So, criteria 1 has been met. Criteria 2 says our function f of x must be continuous. Well, when we discuss the continuity, once again, we are concerned with only the continuity over the interval 1 to infinity. And if you look at the x squared plus 1 in the denominator, there is no chance of x squared plus 1 ever equaling 0. So since there's no value for x that will make this function discontinuous, we're just going to go ahead and call it continuous. Yes, lots of interruptions at Avon High School today. Now, as I told my students many, many times, generally if questions like this are presented in a multiple choice format, this type of writing will never have to take place. You can just visually inspect this nth term expression and come to these 2 conclusions. Now, the third criteria is a little trickier. It's going to cause a little bit more work on your part because we do have to verify that we are decreasing. So the best way to do that is obviously by using the first derivative test. And you can take the derivative here a variety of ways. You can either use the quotient rule or the chain rule. I think I'll elect to use the chain rule, and I might want to at least entertain the possibility of rewriting this f of x as x squared plus 1 to the negative 1 power. Okay, upon doing that, my derivative would be negative 1 quantity x squared plus 1 to the negative 2 power, all multiplied by 2x using that chain rule. And that would simplify to be negative 2x. That negative is going to play a very important role, as you're going to see. And it really doesn't matter whatever x you decide to plug in, that's at least 1 or bigger, we're going to be left with a negative result. Does everybody see that? So we are less than 0 for all x that are 1 and greater. And really, I'm not going to make a big deal out of you use open notation on this left side, closed notation. We've had many conversations both with my students on some of my other YouTube videos that advanced placement exam and the readers really look the other way, and they don't mind if you have a bracket or a parenthesis there. So all the criteria have been set. We know that this function is going to be decreasing. I entertained the possibility of entering this into a graphing calculator, but I've decided not to now. You could verify that it's decreasing that way as well. So now the integral test. Now we got a little BC calculus to do here. The integral test here will look a little something like this. We are basically going to analyze the behavior of the integration from 1 to infinity of this function, 1 over x squared plus 1 with respect to x. And what the integral test says is whatever this does in terms of its convergence or divergence is the same as whatever this summation expression will do. They are one and the same. Okay. The only thing that you've got to be careful about is if you do find that this does indeed converge because the integral, the improper integral, is equal to some discrete value, that discrete value is not necessarily the sum. Right? I can't emphasize that enough. So now it becomes a mini lesson in how do we take the improper integral here one more time. Well, what I've explained to my students in the past is there really is no place for an infinity symbol as a boundary and integration problem. So instead, we'll use a limit process. You can use really any letter that you want. I like to use b when I'm replacing an upper boundary. And we'll simply allow that b to become very close to 0 and focus on the integral from 1 to b. Now at this point, we've got to sort of dust off some old integration formulas. The integration of 1 over x squared plus 1 is an old AB calculus formula that perhaps we remember, and that would be the arctangent of x, the inverse tangent. So it looks like we're all set to complete our fundamental theorem of calculus and run our boundaries b and 1 in. Now remember, the limit statement is still out there waiting to do its job. And we insert b for x, and we insert 1 for x. And now we can entertain the possibility of plugging in infinity for b, I suppose. Can we indeed take the arctangent of infinity? Interesting idea, isn't it? And it turns out that we certainly can. We can do that. Perhaps you have a little bit of knowledge about what the graph of arctangent looks like. Of course, you can verify this on the graphing calculator, but if you do recall from trig class, the arctangent graph has a sort of a shape somewhat like this. Right? It does have a pair of asymptotes here, a couple of horizontal asymptotes. Those asymptotes were formerly vertical asymptotes of the tangents graph. Now they're horizontal asymptotes of the inverse tangents due to the x and y flip-flopping. And hopefully everybody remembers these positions as being pi over 2 and negative pi over 2. Now we're a lot more concerned about the pi over 2 because as our x becomes infinite, we sort of approach this horizontal line that has this value of pi over 2. So anytime you see arctangent of infinity in a calculus class, replace it with pi over 2 every time. And of course the arctangent of 1 is pi over 4. Hopefully that's not giving you a whole lot of trouble. Subtract the 2, you get pi over 4, I believe. Now, when you think back to your improper integration, whenever you got a finite, discrete, an actual value for an answer, you were always told to say that that integral does indeed converge. And that's exactly what we're going to say about our summation. This series does indeed converge. But I'm going to add, once again, as a little side note here, It converges, but it doesn't necessarily converge or add, which is really the same, to pi over 4. In fact, this particular series probably doesn't add to pi over 4, and it really is a little bit beyond the scope of the class that I teach here that will allow us to add this particular series. So we're just left with the fact that it converges, and it's a mystery what it converges to.